Hi everybody, we're going to continue our conversations that we've been having about intramolecular forces and different properties associated with intramolecular forces, and we're going to get into the details of a phenomenon called vapor pressure, and eventually we're going to talk about a sort of separate idea, the idea of phase diagrams. So to this point in class, we've actually gone into quite a bit of detail discussing how intramolecular forces affect boiling points and melting points. Of course, you'll recall that the correlation is that as the intramolecular forces, as the strengths of the IMFs increase, then things like the boiling point will also increase. And again, we've discussed that in class. We've also made mention of a variety of other properties, including viscosity and surface tension. Viscosity is a liquid's resistance to flow, and so if the molecules that comprise the bulk liquid have a lot of intramolecular force, then they'll also have a high viscosity. And surface tension is a liquid's resistance to increase its surface area. So if the liquid molecules would rather stick to each other, they're not going to want to spread out. And so high IMF will also lead to a high surface tension. The thing we're going to focus in on in this video is the concept of vapor pressure. We're going to go ahead and define vapor pressure. I'll show you a cartoon to help you visualize what vapor pressure is. And again, we're going to create a connection between vapor pressure and intramolecular forces. But more importantly, we're also going to quantify that connection. With the other properties like boiling point and melting point, we have correlations, but we really didn't quantify the connections. And with vapor pressure, we're going to do that. We're going to quantify the connection between vapor pressure and ultimately the issue of temperature. And we're going to spend some time in this video talking about some phase diagrams. So let's get right into it. Vapor pressure. What is vapor pressure? Well, vapor pressure is really a property of a liquid. So in my cartoon over here on the right, I have a sample of some liquid water sitting in a beaker. And imagine we can put a cover on that beaker, and at some temperature, and it's important to keep in mind that vapor pressure is always going to be measured at a particular temperature. At some temperature, a certain amount of the water liquid molecules will evaporate. And so we'll have gaseous water vapor sitting on top of the liquid. And over time, the system will reach an equilibrium, as indicated by these blue and red arrows. Water evaporates, water condenses. Water evaporates, and then it comes back and it condenses. Once we've established an equilibrium between the liquid phase and the gas phase, we can then go ahead and measure the vapor pressure, which is abbreviated P sub vap, and that will give us the pressure of the gas sitting on top of the liquid. Now there's a correlation here between pressure, vapor pressure, and intramolecular forces, and I think it's pretty easy to understand. The more that the water molecules want to stay in the liquid phase, the greater the intramolecular forces between them, because they're going to want to stay in the liquid phase, the more reluctant the liquid molecules will be to evaporate. So quite simply, as the intramolecular force increases, as IMF goes up, then the vapor pressure is going to go down. So this is actually an example of an inverse correlation. I think up to this point, everything, all the properties have been going up as the intramolecular force goes up. Boiling point, melting points, these sorts of properties all increase in value as the intramolecular force increases. Now, as you can imagine, I already specified the issue of temperature. There is a connection between vapor pressure and temperature. So if we were to go ahead and heat up, this is an attempt to put a Bunsen burner under the beaker there. If we were to heat up the beaker of water, then surely more liquid molecules are going to go and become gas, right? Evaporate and turn into gases. So then as the temperature increases, the vapor pressure is also going to increase. And it's this connection that we're going to investigate in a little bit more detail and ultimately come to quantify. So here's some data correlating vapor pressures and temperatures. For water, you can see here, for water, as the temperature increases, the vapor pressure, and I've measured it here in torr, or millimeters of mercury, the vapor pressure is increasing. And eventually, we're going to get to that particular temperature for water, 100 degrees. You and I should recognize that, of course, as being the boiling point for water. And so what is the vapor pressure going to be? Well, if you kind of pay attention to where these numbers are headed, maybe you can imagine that at 100 degrees, we're going to get to 760 torr, or 760 millimeters of mercury. So that you should recognize as being atmospheric pressure, standard atmospheric pressure, which really then gets to a more rigorous definition of boiling point. A boiling point isn't when you look at a liquid and you see a lot of bubbles coming out of it, although that's happening at the boiling point. The rigorous definition of boiling point is the temperature at which the vapor pressure of that liquid equals the surrounding atmospheric pressure. I'm going to say that again. The boiling point is the temperature at which the vapor pressure of the liquid is equal to the surrounding atmospheric pressure. There's also one other definition associated with boiling point we should be aware of, and that is something that's called the normal boiling point. Now, atmospheric pressure can change. The boiling point of water here in Hackensack, New Jersey, is right around 100 degrees because we are more or less at sea level, so our atmospheric pressure is usually pretty consistent with 760 torr. But if you go to Denver, the quote-unquote mile-high city, there's some 5,000 feet up in the air, the boiling point of water there is noticeably less. It's in the vicinity of, I believe, about 95 degrees Celsius. And that is because it's going to take less energy, a lower temperature, to get the vapor pressure of water to equal that lower surrounding atmospheric pressure. But then this brings us back to normal boiling point. Normal boiling point is, by definition, the boiling point of a liquid when we set the surrounding pressure to be normal, to be 760 torr. So normal boiling points are standardized to 760 surrounding atmospheric pressure. So the normal boiling point for water in Hackensack, in Denver, at the bottom of Death Valley is still 100 degrees because it's more of a definitional boiling point. All right, let's come back to the numbers I'm showing here in the chart, because what we're going to do is we're going to cartoon the trend in those numbers on the axes on the right. As you can see here, I have pressure and temperature. And if you pay attention to the temperatures and the pressure, you'll see obviously the pressure is going up as the temperature is going up, but it's not going up in a linear fashion. It's kind of going up at an exponential rate. As you can see, when you get to 40 degrees, the pressure is only 55 torr. But then just a few degrees later, up at 90 degrees, the vapor pressure of the liquid of the water has really taken off, going to well over 500 torr. So there is an exponential growth in the vapor pressure of water as the temperature increases. Now, curved lines are pretty, they're fun to look at, they're fun to graph, but they're not very helpful when it comes to making predictions. We would much rather have this line turn out to be linear. And so what we're going to do is we're going to do a little bit of a mathematical trick. I'm going to play with the axes, the y-axis value and the x-axis value, and we're going to be able to actually get eventually a straight line. My red line there is an attempt to draw a slightly straighter line. So how do we get a linear relationship between vapor pressure and temperature? Well, that is shown here. You can get a linear relationship because you have an exponential, so you kind of want to work with functions that are related to the exponential, and so that's going to be the natural log. So if you change your y-axis to the natural log of the vapor pressure, and your x-axis to the reciprocal of temperature, of course in Kelvin, because we want to be on the absolute scale so we don't introduce any negative values, you will then get a linear relationship between pressure and temperature. And because of the way the axes are set up here, we're going to get some nice linear lines. Now, this linear relationship was identified and articulated by a couple of physicists. At this point, I guess we're talking about 150 years ago or so, Clausius and Clapeyron. And so what they did is they correlated pressure and temperature to the heat of vaporization. It turns out that the slope of this line that I have drawn, the slope of this line will give you a physical value, namely the heat of vaporization of that liquid. So in the Clausius-Clapeyron relationship, as it is most commonly articulated, you talk about a vapor pressure P1 at some temperature T1, and a vapor pressure P2 at some temperature T2, and then they are correlated by the heat of vaporization divided by R. That's the universal gas constant. And the value of R you typically want to use here is going to be the one that has joules and Kelvin in it. So that's going to be 8.314 joules per Kelvin mole. And of course your temperatures need to be in Kelvin. So on an upcoming set of practice problems, I'll have you work with this equation and give you different pressures, give you different temperatures. Maybe you'll solve for the heat of vaporization or some permutation thereof. These are good problems to practice because algebraically solving these can be just a little bit complicated because you do have this natural log and you do have this difference of reciprocal temperatures. So working through the algebra to solve these problems is definitely something you're going to want to practice on those materials that you'll get later on. Okay, now we're going to shift gears. We're going to talk about phase diagrams. A phase diagram is another graph that has pressure and temperature on the two respective axes. And what a phase diagram does is it's almost kind of self-defining. It tells us what phase is present at a given pressure and temperature. Here we have the phase diagram for water. Like a lot of things in chemistry, we use water to explain the initial topic. And this is the phase diagram for water. And it makes some sense when you kind of orient yourself. At lower temperatures down here, you tend to favor the solid phase, right? This is ice. At moderate temperatures, right, between 0 and 100 degrees, you're going to favor the liquid phase, liquid water. And then at higher temperatures, you're going to favor the gas phase. And then pressure here, at lower pressures, if you drop the pressure, gas becomes more predominant at lower temperatures. And there's not much of an effect when it comes to the solid phase, as you might expect when you manipulate pressure. Excuse me. All right, so let's make sure we remember a few terms for phase changes. If I go from the solid to liquid, I am obviously melting. If I go from liquid to solid, that's freezing. If I go from the liquid to the gas, I am boiling the material. Gas to liquid, I am doing condensation. Now how about these terms? Do you remember the term from going from a solid to a gas directly? Do you remember what that term is? You see this most commonly with things like carbon dioxide. This is sublimation. And then going from a gas right back to the solid, this is a phase change referred to as deposition. Deposition. Okay, so a couple of other features I want to zero in on when it comes to phase diagrams. Take a look at this point right here. I've covered it up with my S, but hopefully you can still tell that we have three line segments coming together. These line segments, they all represent the equilibrium positions between the two phases they connect. So this line here is the equilibrium line between solid and the liquid phases. All right, and this line here is the equilibrium line between liquid and gases. So if you're at a temperature and pressure that corresponds to being on one of those lines, then the two phase changes, boiling and condensation in this case, are going on at equal rates. Here, melting and freezing would be occurring at equal rates. And then there is a point right here where all three of these line segments, these equilibrium line segments, come together. This is a region referred to as, you can see it right here, the triple point. So at the triple point, all three phases and all 6 phase transitions are in equilibrium. So if you looked at a sample at the triple point, it wouldn't look that amazing, right? You would see solid, you would see liquid, you would see, or I guess you wouldn't really see it, but gas would be present. So all 3 phases are present, and they're all interchanging between each other at the same rate. Another point to bring to your attention when it comes to a phase diagram is this point right here, referred to as the critical point. The best way to think about the critical point is in terms of temperature. So for water, the critical temperature is about 374 degrees Celsius. That is, at this temperature, once you take water to 374 degrees Celsius, it will always be a gas. Sometimes it's also referred to as a supercritical fluid because here it is a gas, but it's also under a high degree of pressure, so it has some properties of a liquid-like flow. But essentially, at this temperature, you're no longer going to be able to condense gaseous water back into liquid as we understand it. It's sort of the kinetic energy point of no return, because at that temperature, the liquid molecules now, gas molecules, will have lots of kinetic energy, and so they cannot be enticed to reform intramolecular forces and reform the liquid phase. Okay, one other point to bring about with the gas, with liquid water here. And oops, I want to get rid of that. I'm going to do some erasing here. Oh, I'm not going to be able to erase. That's okay. I want to zero in on this line right there. Take a look at the slope of that line. You see that it's leaning to the left. The slope of that solid liquid line is indicative of the relative densities between the solid and liquid phases. So consider this. Let's focus in on a point right here. So we are in the solid phase at that particular pressure and temperature. And what if we stay at the same temperature, but we just squeeze the material? So I'm going to try to go straight up from here. And you see that we cross over into the liquid phase. Now, if you imagine compressing a material, you're now going to force its matter into a smaller volume. So it's going to transition to a higher density value. And when it comes to water, when you squeeze the solid and it goes to a higher density value, it also does a phase change. It turns into a liquid. So this negatively sloped liquid solid line is indicative of that weird thing that water does, namely it expands when it freezes, or it contracts when it melts. The density of liquid water is greater than the density of solid because of the expansion when it freezes. All the other phase diagrams we're going to look at, this solid liquid line is going to be sloped the other way. For example, here's carbon dioxide. So you see the solid liquid line is tilted to the right. So that is how most phase diagrams are going to be oriented. So the solid is more dense than the liquid. If I were to start here in solid and squeeze, I would stay a solid. Couple of things to notice about carbon dioxide. Let's see, where do we live on this phase diagram? Well, we live at about 25 degrees Celsius and about 1 atm. So we live right around here on this phase diagram. And so we see carbon dioxide, or we experience carbon dioxide then mostly as a gas, as this phase diagram suggests. And it's not that hard to go ahead and get to the critical point for carbon dioxide. It's a mere 31 degrees Celsius. And CO2 is an excellent example of that process of sublimation, right? You can have solid CO2, which we commonly refer to as dry ice, and at 1 atmosphere, we can see that solid CO2 will easily transition directly into a gas. It will do sublimation. All right, I just want to show you one more. Here's the phase diagram for elemental carbon. Now, elemental carbon is an interesting material. It has a variety of different forms. So I'm showing a phase diagram. We've got the liquid phase, the gas phase, and then you see here two versions of the solid phase, diamond and graphite. When you have different versions of the same phase of a material, those are called allotropes. A-L-L-O-T-R-O-P-E, allotropes. Now, as you might know, there is a third allotrope of carbon called a buckyball, which is a cage of 60 carbon atoms. And there have been also different varieties made, like bucky tubes and things like that. So the phase diagram I'm showing here is not actually entirely up to date. A couple of things I want to point out about this phase diagram. Point one is we have here our triple point right there, the three phases coming together. There also seems to be another triple point up there. But this second triple point is a little bit more unique. Here it's two solid allotropes coming together with liquid. So I guess by the strictest of definitions, that may not be considered a triple point because we don't have all three phases present. But, you know, it's perfectly fine if you refer to that as a triple point. Just appreciate that this triple point and that triple point are triple points for different reasons. All right, the other thing we can point out is, again, where do we live on this phase diagram? So temperature, this one's in Kelvin, so we're way over here on the left. And pressure, this is in pascals, and so again, we're down here towards the bottom. So we're somewhere around here on this phase diagram. And so you can see that the preferred form of carbon where we live is graphite. Which brings up an interesting question. We all know that we have diamonds, right? When I got engaged, I gave Mrs. Dr. Crane a diamond ring. Well, we'll say it's diamond for the purposes of this conversation. Okay, it is. It's a diamond ring. So how was I able to give Mrs. Dr. Crane a diamond ring when we got engaged if we live down here? And that speaks to the kinds of information that we get from a phase diagram. A phase diagram gives us thermodynamic information. Namely, it tells us what is possible under a given set of conditions. It doesn't tell us any information about the rates of any changes. So we're not getting rate information. So that diamond ring was formed, in lower layers of the Earth's crust. So it was formed under high pressures. And it got mined and it got brought to the surface. And so eventually that diamond ring is going to make its way towards graphite. My wife's diamond ring is turning into essentially pencil lead, pencil graphite. The good news is the rate at which this happens is very, very slow. So I think the Earth will probably end up being consumed by the sun before we have to worry about our diamonds turning into pencil lead. All right, so that's a little bit then about vapor pressure, quantifying vapor pressure through the Clausius-Clapeyron equation, and looking at phase diagrams and appreciating, based on pressure and temperature, what phase is going to be preferred, and getting into some of the details of phase diagrams in terms of the different phase changes that you can do, the different points on a phase diagram, and some of the thermodynamic information you can get from a phase diagram. That's all for now. I will see you later.